So today, we are going to dive into one of the most incredible biological machines on the entire planet, your muscles. We're going to pull back the curtain on the absolutely stunning science behind how every single movement you make, from a tiny blink to a powerful jump, actually happens. I mean, really think about that for a second. That simple act, lifting your coffee, involves a biological process so ridiculously intricate it's happening at a molecular level, trillions of times over, in almost perfect unison. So what is really going on in there? Well, let's find out.
You know, what's kind of funny is where we even got the word muscle. Apparently, ancient observers thought that when you flex your bicep, it looked like a little mouse, or mus in Latin, scurrying around under your skin. It's a great image, right? But how does that little mouse generate so much power? Okay, so before we zoom way into the microscopic world, we need to get the big picture. Because I guarantee your muscles are doing a lot more than just lifting things and helping you run. They are absolutely fundamental to pretty much everything your body does.
Yeah, of course, movement is the most obvious job, but your muscles are basically working 24/7. Right now, as you're sitting there, they're maintaining your posture. They're constantly making tiny adjustments to stabilize your joints so you don't just collapse. And get this, they're generating a huge chunk of your body heat, acting like a built-in furnace.
And to be able to do all that, muscle tissue has 4 really amazing properties. First, it's excitable. That means it can get a signal from your nervous system and actually respond to it. Then it has contractility, which is its unique superpower to shorten. It's also extensible, so it can be stretched out. And finally, it's got elasticity, which lets it snap right back to its original length after being stretched.
All right, now that we've got the lay of the land, let's start zooming in. I want you to picture a really thick electrical cable. You know how it's not one solid wire, right? It's a big bundle of smaller wires, and those are made of even finer little strands. Well, your muscles are built in almost the exact same way. It's a nested design.
And you can see that design perfectly right here. The entire muscle is wrapped up, but inside, you can see all these separate bundles. And if you could zoom in on one of those bundles, you'd find the individual fibers. It's literally like a biological Russian doll.
So let's just quickly walk down through that hierarchy. Now, don't get hung up on the fancy names, just think about the layers. You've got the whole muscle itself. Inside that, you have bundles called fascicles. Inside those are the individual muscle fibers, which are the actual cells. And then finally, deep inside each cell, we find the real engines, things called myofibrils. Okay, we've gone past the muscle, past the bundle, past the fiber. We are now inside the myofibril, and we've arrived at the engine room. This little thing is called the sarcomere. This is the fundamental unit that actually generates the force and creates all movement.
And this image shows the magic of contraction perfectly. Look on the left, that's a relaxed muscle. You can see these clear, distinct light and dark bands. Now look to the right at the contracted one. Do you see how the two ends, the Z-lines, get pulled closer together? The light bands shrink and can even disappear completely. That shortening action, repeated millions and millions of times, is what a muscle contraction is.
So, just to put a formal definition on it, the sarcomere is that basic unit of contraction, running from one of those Z-lines to the next. And it's the repeating pattern of all these sarcomeres all lined up that gives skeletal muscle its classic striped or striated look.
Okay, so we see that the sarcomere shortens. But that just leads to an even more amazing question. We're looking at tiny little protein filaments. How in the world do they generate enough force to actually pull on each other? Well, the answer is a kind of beautiful molecular dance.
So, let's dive down one last time, to the molecular level, to see the absolute climax of our story, the power stroke. This is where we meet the tiny protein dancers, whose incredible choreography is the source of all your strength. Let's meet the cast of characters. First, you've got myosin. These are the thick filaments with little heads on them that do all the pulling. They want to grab onto the thin filaments, which are called actin, but when the muscle is resting, a block of protein called tropomyosin is in the way. It's held in place by another protein, troponin, which acts like a lock. To open that lock, you need the key, calcium, and the whole show is powered by the fuel, which is ATP. So here's how this dance starts. Step 1. An ATP molecule, our fuel, latches onto a myosin head. The head then breaks that ATP down, which releases a burst of energy. That energy is used to cock the myosin head back, kind of like pulling back the hammer on a gun. It's now in a high-energy, ready-to-fire position. Now for the trigger. A signal from your nerve tells the muscle to release calcium. That's our key.
The calcium rushes in and binds to troponin, the lock. This causes the troponin to change its shape, and it yanks that trypomyosin blocker right out of the way. All of a sudden, the binding sites on the actin filament are exposed, and that cocked myosin head, it immediately snaps forward and grabs on, forming what we call a crossbridge.
And here it is, the moment of action, the power stroke. As soon as it's bound, the myosin head pivots with incredible force. It pulls the thin actin filament along with it, sliding it toward the center of the sarcomere. This is the tug in our molecular tug of war. And as it pivots, it lets go of the used-up energy molecule, ADP.
But wait, the myosin head is now struck to the actin. How does it let go so it can grab on and pull again? Well, and this is the cool part, a brand new ATP molecule has to show up and bind to the myosin head. So ATP isn't just the fuel to cock the head, it's also the key to release it. The second that new ATP binds, the head lets go, and the cycle is ready to start all over again, as long as there's calcium and ATP around.
Wow. Okay. We've gone from the whole muscle, down through the bundles, into the cell, and all the way to the molecular dance of tiny proteins. Now, let's zoom all the way back out and see how this incredible process actually translates into the movements we make every single day.
So, when you get right down to it, our muscles contract in two main ways. You've got isotonic contractions. That's what you probably think of. The muscle actually changes length. It shortens or lengthens to move something, like when you curl a dumbbell. But you also have isometric contractions. That's where the muscle fires up and creates force, but its length doesn't change at all, like when you just hold that dumbbell steady in midair.
And we can actually break that down even more. So lifting the weight is a concentric contraction, the muscle gets shorter. But, and this is important, lowering that weight slowly and with control is an eccentric contraction. The muscle's actually lengthening, but it's still under tension. And just holding it perfectly still, that's our isometric contraction. It's the same muscle doing three totally different kinds of work.
And to add just one final layer of complexity here, not all muscle fibers are the same. We basically have two main flavors. On one side, you have slow twitch fibers. These are your endurance athletes. Think of a marathon runner. They are super resistant to fatigue. On the other side, you've got fast twitch fibers. These are built for pure explosive power. Think of a sprinter or a weightlifter. They're incredibly strong, but they burn out really, really fast.
This quote really just sums it all up perfectly. At its absolute core, a muscle is a biological engine. Its special, defining feature is its ability to take chemical fuel, ATP, and convert it with mind-boggling efficiency into mechanical energy, into force, into movement.
So the next time you do even the simplest thing, pick up your phone, type on your keyboard, or lift that morning coffee, just take 1 second and appreciate what's really happening. A silent, perfectly coordinated storm of trillions of molecular power strokes converting chemical energy into motion. It's happening inside of you right now.